Welcome to day 12. Homework will be in the calendar packet, page 1 and 2. I would suggest doing it on a separate sheet of paper to make sure you have enough space. And today is to introduce the stuff for the second half of the unit, which is Taylor and Maclaurin polynomials. So first off, I want us to think about what method do we currently have from calculus that allows us to approximate the function near some given point. And the thing that you've been using since last year is our linear approximation. And with linear approximation, the idea is that close to the point of tangency, the linear approximation of your curve is a good representation of your curve. Well, we're going to expand on that idea today. So we'll want to be in your notes packet on the day 12. And I want you in this top one to think about what function is graphed here. So hopefully you thought maybe y equals x. That's what I was hoping you would say. But imagine we zoomed out a bit. So that box is what we were just looking at. Sure looked like y equals x, but without a scale, we really didn't know. Actually, that was a curve kind of like this, which appears that it might be cubic. So what this focused on was the idea of local linearity. In calculus, there's an idea that if you zoom in far enough, pretty much every function can look linear as long as you zoom in far enough. Now, that's not true at places that aren't differentiable, like for example, the point on an absolute value. If you zoom in far enough there, that's not going to look linear. But on spots where things are continuous and differentiable, then that is the case. So it appears that we've got some cubic function going on here. But if we flip the page and zoom out more, that actually wasn't a cubic function. So again, we've been tricked. Hopefully you recognize that that looks more like our sine graph. So the box was what we were viewing before, and now we've zoomed out more. So we actually already know that y equals x is a good approximation of sine x near the origin. And there's two reasons why we know that. One, we've seen the limit as x approaches 0 of sine x over x. You've seen in several different scenarios that that's equal to 1. Well, if something divided by itself is 1, it means they're essentially the same. So when x gets close to 0, those are really, really similar. That's why we get 1 back. Another reason for that is if you wrote the equation of the tangent line, your derivative of sine is cos x. If you evaluate that at x equals 0, your slope is just 1. So if you have y minus 0 is equal to 1 times x minus 0 using our point and our slope, that's just y equals x. So y equals x is the tangent line approximation of sine at x equals 0. But as we move further away from x equals 0, that tangent line is not as good of an approximation. So what we're going to try and do, because that box looked kind of cubic, we're going to see if rather than just using lines, if we can find a polynomial that does a better job of approximating sine for a bigger interval. So some things to note before we start making guesses. One is that the y-intercept's 0. So we shouldn't have any constant term on our cubic. Second is it's an odd function. It's symmetrical about the origin. If you spin it 180, it looks the same. So if it's an odd function, we wouldn't have any squared term in there. And then lastly, our end behavior. Our cubic function, this was the part that we thought looked kind of cubic. So notice that end behavior, on the left it would be going up, and on the right it would be going down. Well, that end behavior would match with a cubic that had a negative x cubed. Because the x cubed would control the value when x goes to infinity, and when we have big positive numbers, we would want that to get negated so it heads down on the right. And the reverse would happen on the left. When you put in big negative numbers, would make it go up. So those are a couple things to notice. So let's start making some guesses. Let's say we just had positive 1 for x and negative 1 for x cubed. The red line graph there is at y equals x, our original approximation. X minus x cubed is the green one graph there. Well, if you notice, that seems to bend too quickly, bends away from the sine function. It doesn't ride it for long enough. So let's make an adjustment. What if we, over on the right, change the coefficient of the x cubed to negative 1/10? Well, notice now that green function, our polynomial, it's not bending enough. Sine is bending too much. So if you play around for a bit, something that would seem to work kind of nice would be something like negative 1/6. So if you look at the bend of that, it seems to hold on to the sine graph for longer than the negative 1 did. And it's not above the bend like the negative 1/10 is. So it looks like negative 1/6 is better than those other two. And if you looked at the table and compared sine x and our x minus 1/6 x cubed, notice at 0.2 they're really close. 0.4 still reasonably close. As we get further away, it's not as good of an approximation. But when we're within 0.4 or so, it's pretty good, it seems like. And even visually on the graph, you can see that the cubic is riding the sine graph pretty good. Well, can we do better than that? So because sine has lots of bumps to it, because of its periodic nature, it might make sense to add some additional terms on that would still make it an odd function, that would still make it work the way we want. So here we've added on 1/20th x to the 5th. So another odd power, so it's still an odd function. The red one was the cubic we had. Now we have a 5th degree, and notice it's holding on to the sine function for even longer. So it appears that's an even better approximation. Well, let's see if we can keep going. So there's a 7th degree one. So the red one on my screen was the one that the 5th degree one. The green one is the new one, the 7th degree one. Notice it seems to be holding on even longer. Well, we can keep going. Look, there's a 9th degree polynomial, and that's holding on really good past -3, so even better than the 7th degree one. So it appears like we could keep adding terms. Well, where are these numbers coming from in the denominator? Are they just random? If we flip to the next page, we have two things. We have an 11th degree one, which is now holding on to it even more. It's holding on to it beyond 4 and -4. And then there's a 13th degree one that goes even further, but notice I've written the denominators differently there. 6 is really 3 factorial. 120 is really 5 factorial. 5040 is really 7 factorial. And now we start to see a pattern that emerges. So from this, you could probably keep adding terms forever if you wanted. We could do minus x to the 15 over 15 factorial, plus x to the 17th over 17 factorial. And it would just keep wrapping around the sine function. So this is kind of amazing. Hopefully it's kind of mind-blowing that there's a polynomial that would do such a thing. So if we go down to the bottom, a couple things that we want to think about. Well, what makes a polynomial a good approximation? How many terms would we want to go out to be satisfied that it is good? Also, where are the factorials coming from? How is it figured out that those factorials in the denominator made the good approximation? So these are things that over the next few classes we will investigate and we will figure out. But for now, we're going to see if we can write a general term for this sine polynomial. Now, one thing to note, we're going to have the starting term be n equals 0. And we'll see eventually in the coming days why we would want it to be n equals 0. Well, notice we're going even, or positive, negative, positive, negative. And because we're alternating signs, we're going to have a -1 in there. we're starting with n equals 0, and we want the first thing to be positive. So we probably want to have that raised to just the n, because when you put an even in, it'll come back positive. Well, now let's think about our powers of x. The powers of x are going up 2 each time, so we're going to need something with 2n in the exponent. But when you put in 0 for n, we get back 0 in the exponent, and we wanted 1. When we put in 1 for n, we get back 2, and we wanted 3. When you put in 2 for n, we get back 4, and we wanted 5. So we're always 1 short, so the adjustment we need to make is just add 1 on the end. So now when we sub in 0 for n in the exponent, we get back 0 plus 1, which is 1. When we sub 1 in, we get 2 plus 1, which is 3, and so on. Well, the denominator should be easy now, because the factorial just matches that exponent. So we'll have 2n plus 1, parentheses, factorial. So these polynomials that we are building, if we go to the next slide, are what are called Taylor polynomials, named after a guy named Brooke Taylor. Every single Taylor polynomial will have some center. And the one we were just looking at with sine, the center was x equals 0. Center won't always be x equals 0, but it was in this case. If you have a Taylor polynomial centered at x equals 0, they're actually called Maclaurin polynomials. And it's after Colin Maclaurin. On the AP, it will use the terminology, say, find a Maclaurin polynomial, and that is conveying to you that we know the center must be at 0. So that's a key fact that we want to know. If we're working with a Maclaurin polynomial, we know our center is at x equals 0. So it's just some terminology. That polynomial that we have below there, we would say that is a 5th degree Taylor polynomial centered at x equals 0. Or because it's centered at 0, we could also say it's a fifth degree Maclaurin polynomial. So by knowing that a Maclaurin is centered at 0, it just reduces the amount of information that we have to write about it. So this is really cool that we've got a polynomial that can match some function that's not a polynomial. But why is this helpful? If we go down to the bottom, we see that polynomials are nice to work with. At worst, if you sub in a nasty number, at worst you're going to have to multiply it out a bunch of times and then add some stuff together. So 2.7, yeah, it wouldn't be awesome, but you could work through 2.7 cubed by multiplying it out with your multiplication algorithm. Same thing with squared, and then add everything together. Okay, it would not be terrible. But if you had, say, sine of 2.7 or e to the 2.7 or square root of 2.7, those would not be that nice to work with. So if you can write those other functions in terms of a polynomial, that makes life a whole lot easier. So if we move on to the next slide, so take sine of 2, for example. Sine of 2's actual value is 0.909. P5 is meaning a Taylor polynomial of degree 5, or sometimes said a 5th degree Taylor polynomial. So the subscript of that capital P tells us what degree it was carried out to. Okay, so maybe we'll write that down here. So this is a 5th degree Taylor polynomial. So compared to like some of the other stuff we've seen, that's not that close, 0.909 to 0.933. So what could we do to make this better? Well, we have two options. We could keep adding terms, because we saw as we added terms, it was a better approximation in a bigger window. Or you could adjust the center. So this one, I don't think I specifically stated it there, but this one was from the one that we built, which was centered at 0. Well, 0 is not that close to 2. Maybe you take something like pi over 2. 3.14 divided by 2 That's like 1.5 and change. That's closer to 2. So your window that it is a good approximation is more likely to surround 2 than when your center is at 0. So those are two ways that if your Taylor polynomial is not as good of an approximation as you would hope, you could make an adjustment. So big thing so far. Your Taylor polynomial will always match the function perfectly at the center. As you move away from the center, you lose some accuracy. If you want to gain accuracy, you can add more terms. So 3 big ideas that we've seen so far. Well, we've only seen one Taylor polynomial. We've seen it for sine. But a big idea in this half of the unit is using what we know to create new things. So let's say we want to create a Maclaurin polynomial for cos x. Maclaurin, again, means we're centered at 0. We could do trial and error like we did for the sine one. Or we could use some calculus. We know that cos is the derivative of sine. So let's take our sine Maclaurin polynomial. So we had x to the first over 1 factorial minus x to the third over 3 factorial plus x to the fifth over 5 factorial and so on. Just so you can see it with the factorials written out there. We've got the 3 times 2 times 1, the 5 times 4 times 3 times 2 times 1. Well, x to the first over 1, its derivative would just be 1. In our second term, if we multiply the 3 out front, the 3's will wipe out, and we'll have minus x squared. So that'll come out, the 3's will wipe out, over 2 times 1, which is just 2 factorial. Plus, if the 5 multiplies out front, the 5's will wipe out, and we'll be left with x to the fourth over 4 factorial. Then we'll have minus x to the sixth over 6 factorial. Plus dot, dot, dot. Let's think about our nth term. So 2 to the n plus 1 would multiply out front, divide out the 2 to the n plus 1, so we will have negative 1 to the n times x to the 2n all over 2n, the whole thing factorial. And just like before, this is starting with n equal to 0 for this general function. And we'll, again, in the coming days, see why we would want that. So, if you are given something that you want a Taylor polynomial for, think about if one of the things you already know, you could do something to it to get that new thing. Now, by do something to it, we're going to always want to think of derivatives, integrals. Could you sub in something that could create that from something we already know? So if we go down to the bottom, just a visual of this cos one. So when n is equal to 0, we would just get 1. Well, that is our linear approximation of cosine x equals 0. When we move out another term, notice it matches better. Move out another term, n equals 2, matching even better. And as you keep going, notice how it is wrapping around that cosine function. So it is matching it very well. If you go to the next page, okay, just a few more of those for cosine, again showing that it is matching it very well. And the table is just showing that numerically. So you will want to memorize the Taylor polynomials for sine and cos. They're going to be 2 of our most common ones. And it might seem daunting, but a couple things that'll make it easier. First, sine's an odd function. Notice all of the powers and factorials are odd. Cos is an even function. So notice all the powers and factorials are even. Use its y-intercept to help figure out what should come first. Well, sine's y-intercept is 0, so notice we start with a variable. Cos's y-intercept is 1, so notice it starts with 1. The first term of each is its linear approximation. So sine's linear approximation is y equals x, cos's is y equals 1, and that's the first one there. And then the signs just alternate in both cases. So we're going to use the idea of using something we know to find something new. And we want to find an 8th degree Maclaurin polynomial for cos x squared. Well, cos x squared is just cos x with an x squared filled in. So we've got written out here our cos x Taylor or Maclaurin polynomial, or we could have said a Taylor centered at 0. So what we're going to do is just everywhere there's an x, we're going to fill in an x squared. So that becomes x squared squared over 2 factorial, plus x squared to the 4th over 4 factorial, minus x squared to the 6th over 6 factorial, plus x squared to the 8th over 8 factorial, plus dot dot dot. And then I'm going to write this as negative 1 to the n. We'll have x squared to the 2n over 2n factorial. So I'm going to just keep writing this down here for a second. So that's really equal to 1 minus x to the 4th over 2 factorial, plus x to the 8th over 8 factorial, minus x to the 12th over, oh wait, sorry, that's not 8 factorial, that's 4 factorial, minus x to the 12th over 6 factorial, plus x to the 16th over 8 factorial. And our general term, this would be negative 1 to the n. We would have x raised to the 4n over 2n factorial. Well, when do you stop? They want us to do an 8th degree polynomial. So our 8th degree would be this right here. So our answer is just 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial. And that would satisfy finding our 8th degree Maclaurin polynomial. So that satisfies the first part that we want. Now the second part of this was to use the polynomial to approximate f of 0.4. So just our notation, the f means the actual function. So if we were to plug it into the actual function cos x squared, and the p is saying use the Taylor polynomial. Well, if we plug it into the Taylor polynomial, because that's what we're intending to use, we get 0.987222730 and so on. Now, just for curiosity's sake, if you plug 0.4 into the original function, you would have had 0.987222728 and some other stuff. So matches pretty well for a long time. And we only went out, in reality, 3 terms there. So last thing for today, we're going to use the Taylor polynomial for sine to evaluate our limit of sine x over x as x approaches 0. Now we all know that the answer of that, but we're going to see that Taylor polynomials can be used to do it. So limit of sine x over x as x approaches 0, if we're using the Taylor polynomial, we could write this as x to the 1st over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot 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 all over x. Well, that's going to become limit as x approaches 0. The powers are going to go down by 1 for all of them. So we're going to have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus dot 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 dot. Well, now as x approaches 0, all those terms other than the first will head to 0. So this is just going to equal 1. So another really powerful thing that we can use Taylor polynomials to evaluate limits that might be tricky. So big ideas, our Taylor polynomials are centered at some value. The Taylor polynomial matches the actual function at the center. As you move further away, it is not as accurate. To get more accurate, you can always add terms. We can use our Taylor polynomials for things we know, like so far we just know sine and cosine, to then find other things that you could maybe get by doing derivatives, by subbing things in for x, by doing limits. So all tools that can be used with the Taylor polynomial to approximate other things. That's it for this video. Have a great rest of your day.